Good question. So depending on how you look at that, and the argument, the conclusion is different from one to another. If we just simply use time dilation formula, then you can see that. So basically, this paradox is work based on the time dilation. This consequence. Do you remember the consequence of time dilation and the length contraction in Einstein's special relativity, time dilation? So they for the first time since Einstein, and people argue that the time is different, right? Do you remember that transformation? So we got x prime, t prime, and equal to, there has a gamma factor here, and it's do that properly. Do you remember we discussed the Lorentz transformation? No?
Yes.
Yeah, that is v c square. Okay. So this transformation is based on Einstein's assumption that the light speed is the same everywhere. That is the Lorentz transformation. So if you want to know if you know the time in one frame, and then the time in another frame would be dependent on the relative speed. Right? So this is Lorentz transformation. This is more accurate. So this is called Lorentz transformation. Which gives exactly dependence of the different time and position in different frame. However, the formula for the time dilation, should I say, this is the first, this is the time dilation. Can we just rewrite this? Time dilation is just give you the, provide you with formula directly. That's what many textbook does so. So the first topic is relativity is one is Lorentz transformation, which is accurate. Transformation. Okay, another idea is just use time dilation formula. Time dilation formula to discuss this issue. So time dilation just gives you the simple formula. Time t is equal to gamma multiplied t prime. Do you remember what gamma is? When you study special relativity, we always use this gamma factor.
Is it?
Yeah, square root. You know this factor?
Yeah.
That's v squared. You will see this factor everywhere when you study Einstein's idea. However, in high school, they didn't taught students about Lorentz transformation, so they only make their discussing by using the time dilation formula. What does that mean? The time dilation formula. If you have the in this context, if you have the two twins, twin brothers, if the one is, can we just make this idea? So this is Earth, right? This is one frame. Another is a spaceship. So you can imagine there's a spaceship flying away from the Earth, right? And what happens that we know that if you have a twin, just draw some graphic. So this is this twin, can we call it A? This is B. Okay, this is B. So if there is a spaceship, this is a spaceship is moving, spaceship. So moving at a constant velocity relative to a, can we see that is a velocity? And before Einstein, and there's no such issue about they were just getting older at the same rate, right? Because before Einstein, we believe that the time on the different frame are the absolute. Can you see? He can carry a clock. He also can carry the clock, right? So therefore, their time, we just symbolically draw this time. They should, if we just start at the same time, and the time you read must be pointed at the same position, right? But not so, according to Einstein. Can you see? I just exaggerate that a little bit. So according to Einstein, special relativity, the time you read here is called t. And the time you read, you think that time, t prime, from A. So what A think about the time? Does it make sense?
Yeah.
So A will think, well, I can use the formula. Say time dilation, you have two formulas, right? One is the Lorentz transformation. Another is use the time dilation formula. Okay. So if you, because according to Einstein, so basically time dilation suggests that the t is not equal to t prime. So what would be the case if they have journey? So they start from journey here, and they go all the way to a non-distance travel to say go to another go to the other side of galaxy, right? And so what would happen? Because their time is different now. So what would happen? So for example, when 1 year after 1 year, and the twin A is old 1 year old, right? But what would be the age of the twin B? Because we have make judgment from the from Einstein's formula. This is Einstein's formula. Okay. So to give you some idea is that certainly in this case, I just categorically say, yeah, according to A. So according to A, so that is a observer A, observer R will think that my time, according to Einstein, is the time getting slower, basically. So therefore, and he will get older faster, and this time is slower. So because it becomes slower, so because according to him, that he will predict that the time on the other side will be. If you can take example, can we just consider example if let's just consider example. If velocity is equal to a constant, say equal to did we use can we use 6, 0.6? C, 0.C. Can we work out what is gamma? Do you want to try? What is gamma if the velocity is 0.6 multiply C? So you can use this formula. Can you see?
So it's 1 over 0.2.
Yeah, you have to, you put all this number here. So this is one take. So velocity is 0.6 C, right? Divided by C and square. Can you use a calculator to work out this number? Must be a number larger than 1. Twin parallax.
1.25.
1.25, yes. Okay. So obviously, you see, in this particular case, one time is shorter, one time is longer. Depending on how you use this formula, right? Depending on how you use this formula. So basically, the if the basically these two times will be different.
Mhm.
So the paradox says that if you follow this Einstein's idea, can we just use this particular case? So in our case, this is a special example. In this case, so what is exactly the relation between t and t? So from this result, we can argue that the t is equal to 1.5 t prime. You see.
Mhm.
For example, if t is 1, can you see? And
Yeah.
then t1 will be longer. See? Here is something we have to get familiar. Yeah, this is the time dimension notation is use a proper time. Oh, there's another issue. But never mind. Can we just use this formula for time being? If t is 1, t prime will be 1.5. Do you agree?
Mhm.
And if the t is 2, and t prime will be 3.1. Can you see? It will be 3. Can you see?
Yeah.
And so on. So you can see somehow the age will be different because we just count the time in order to find how old we are. Do you agree?
Mhm.
So one of twin brothers should getting older faster. Does that make sense?
Yeah.
So this is one consequences of the Einstein's time dilation formula.
Mhm.
So if you but you have to be careful. When you use this second time, and another form, this formula actually can be written as a t equal to t0. Okay, many textbook use this one. I will double check that. So these they have used a proper time. So that's very confusing. C squared. So t is called the proper time. The proper time. Have you studied proper time? No. They were mentioned that without explanation. I will check that.
Yeah.
You
And
see,
I think t, like just t is dilated time.
Well, they will argue that the proper time is always the longest. They have the argument for that. And let's go to relativity. Yeah, that is a very commonly discussed issue, but without using Lorentz transformation. Let's talk about this formula. So basically, yeah. So this is t prime, the t dash is called measure as a proper time. So the definition of this textbook definition. Sometimes they use t prime, sometimes they use t0. And so delta t, can you see the time in interval t measured by an observer moving with respect to the clock is longer than the time interval. This is a moving clock, sorry. And by the observer at the rest, respect to the clock, because gamma is always greater than unity. That is the time. One time interval is larger than others. So from this result, we can argue that the t prime, so you have assigned a proper t prime to which it's just, they're actually talking about two references. There are two frames, okay? One is the frame A, so the frame, so relatively, frame B is moving, right? So frame B is moving, so therefore they argue that the time we're getting longer. So that's what we have observed here, can you see? Because frame B is getting, so that is why, so this time getting faster.
Yeah.
Sorry, the time getting longer. The clock is slower, can you see? The clock is slower. So if you just count, so that is the paradox come from, can you see? So this is a time used by frame A, can you see? This brother A, this brother B, can you see? This A, this is B. So what would happen if after many years of this travel and after goes and return, okay, presumably the velocity, relative velocity is the same, and the time dilation formula doesn't account the direction of speed, right? So therefore, what would happen that is that they found that the time on the Earth, for example, he's 2 years old, but his brother would be 3 years old, older than and at the beginning when journey start. Can you see that? So this sounds very incredible, isn't it? How could one's age change with the relativity? So it is a paradox. So it cannot be true, but by using Einstein's dilation formula, it does predict that the clock at different frames how to tick at the same rate, different rate. Questions?
Yeah. So when the how do we know that? How do we prove that?
You can. This is thought experiment. You cannot prove that. So this is consequence of time dilation, and a paradox can hardly experimentally prove, because in order to prove that, so this is very exaggerated case. Okay, so this is a hypothesis. Can you see? When we say that when we say the spaceship travel at that speed, what does that mean? So which means that in this case, the velocity is equal to 0.6 multiply 3 multiply 10 to the power of 8 meter second, or that is 1.8. Can you imagine any real flying object, man-made flying object, can travel as fast as that?
No.
No, no way, right? And if we just go to a second scenario, just because can we say if we just consider the fastest car, for example, right? The velocity would be, can we say, if you want to try some unit transformation conversion, for example, the racing car, right? They can probably 300 kilometers per hour. That is very fast, right? That's, or you can go faster, such as magnetical. Can we just count airplane? So airplane can travel even faster, right? Can we say, can we count 3,000? Can you see? Can we just count 3,000? This is pretty very fast now per second, right? I'm trying to say that how can we make sense? Can we just consider 300 kilometers? That is the fastest car you can imagine of. So because our limit, do you know the limit of speed on the highway is 100K, right? 100K, that is hours. That's hour. So this is 3 times than that speed limit. So if we convert that, can we convert that into meter second? So that is a multiply. I have to multiply 1,000 here, divided by 3,600. That will convert it to meter per second. You follow me?
Yeah.
So this is roughly. So that if you just roughly write that, it was just 3 multiply 10 to the power 5, and that is a 3 multiply 10 to the power 3. 3, can you see? So that will give very close to this just 10 to the power of 2, 100 meters. So that is 100 meters per second. That is speed for the very rapid car, racing car. Okay.
Mm-hmm.
Now, if you use this scenario, and can we work out the gamma again? Can we work out what gamma is? Gamma would be 1 take, that is 10 to power 2, right?
Mm-hmm.
And for the night speed is 3 multiplied 10 to power 8. Wow, can you see?
Yeah.
Now, can you work out what is the gamma now this time? Must be very close to unity, right?
Mm-hmm. 1.000000167.
Oh, yes, almost 1. Okay, almost 1.
Mm-hmm.
So in this case, the time is almost the same. Do you agree? Almost no change, right?
Mm-hmm.
So that's a good question to use any experiment to test it, this special relativity prediction. It's
Mm-hmm.
very difficult, right?
Yeah.
You see, that is all about this twin paradox. However, if you use Lorentz transformation, and the outcome will be different.
Mm-hmm.
They can actually, I did that some time ago, that if you want to use Lorentz transformation, let me see. Let me show you what I have done. Yes, actually, I make a short video. Yeah, I can find this video for you first. Yeah, we can, because I can't remember. Did we talk about the Lorentz transformation last time? Yes or no?
No.
Oh yes. If not, probably have to. I will probably 1 moment. Yeah. So this is a video I made about this issue. Can you see this side? Can you see my side?
Yeah.
And so basically, this is how to use Lorentz transformation to discuss this issue.
Mm-hmm.
So here, this is a brother. So this is a twin brother A and B. Can you see?
Yeah.
I divided that journey into 2 parts. One is away from the Earth at a constant velocity. Another is return to the Earth again at same velocity speed, but opposite direction.
Yeah.
And what I do, I just will give very briefly show. So instead of using Einstein's time dilation formula, I use Lorentz transformation I mentioned here. You see?
Mm-hmm.
I don't have to go to detail. I just let you know that I discuss this two-way journey. In the first half of journey, by using this Lorentz transformation, I can switch off this. I obtained that the time, I obtained this result. So T is larger than T prime in the first part of journey. So this is how, if you're interested, you can use Lorentz transformation. So indeed, what does that mean? That one brother is getting older faster.
Yeah.
So in other words, the B aging slower because the time is slower. The time is slower, right?
Mm-hmm.
So in other words, the brother on the Earth is getting slower. However, if I consider another half of journey on the way back, then we still use Lorentz. If we still use Lorentz transformation, and there is a sign change, can you see?
Mm-hmm.
So this detail cannot be discussed by using that time dilation formula. And to cut the story short, so what is my conclusion? After they return, on the way back, we found that, can you see? We were found that the time prime is longer than the t. It's opposite. So depending on the journeys, these away or backward, the relation between these two clocks are different according to Lorentz transformation. So if you're interested, you can watch this video. So what it does mean that this is a proof that there's no twin paradox.
Yeah.
You see, depending on
the thing would like even itself out.
Yeah, that's even out. Yeah, that's so. Therefore, there's however, I don't think everyone accept my proof because I noticed that many teachers accept this paradox as because you know why? Because they only if you only use Einstein's, let's just stop here. If you only use Einstein's time dilation formula, then you can only get this formula. Can you see? In respective which direction does the twin brother travels?
Yeah.
So what does that mean? Which means that you can accept there is a twin paradox, right? If we just using the time dilation formula. Okay. Now, another part of they didn't tell students is that if we know the Lorentz transformation, if we apply the Lorentz transformation between the two time, then we will find that there's no twin paradox.
But would they be like increasing and decreasing at the same rate?
Well, the only thing we can argue is that we have to you see, Lorentz transformation is very much dependent on the another thing you have to consider when you compare with time. You have compare with the let's go to next page. So when we use Lorentz transformation, so this is this is t. Sorry, this is you have to consider the coordinate. Very good question. So to get x prime, the t prime is equal to. So this is this is two variable. Multiply the gamma. This is 1 negative v c square, and that is a negative v. So this is the product of matrix x t. Do you know how to write that as a simultaneous equation? So 1 multiply x is x, right? And negative v multiply t. So that is the first transformation. For the time, which uses this one, we can write the time second. Okay, we can put x in front. So that is, doesn't matter. We can put this as a t first. That is x, c square x plus t. Can you see that? So in this way, you can see that there's no, from this one, you can, there's no simple relation between t and t prime. Okay. So what that means, no simple relation, between t and t prime. Can you see? If we do want to write that down, can you see? If we just from this formula, if I just rewrite the formula, what we can see, so there is t prime here, okay? From here, what we can see, the t prime is equal to gamma, right? Can we just put the t in front? Plus, minus, sorry, vc squared plus x, all right?
Mm-hmm.
The only simple relation we can argue is that if we just let x equal to 0, that is the position of the clock. Let x equal to 0, then we can get this simple relation. Can you see?
Mm-hmm.
Can you follow me?
Yeah.
So that what does that mean? That the time dimension formula is conditional. So can we return to this time dimension formula here? Can you see that?
Mm-hmm.
In other words, you cannot just discuss the time, the difference between the times in 2 frames of reference without mentioning where is the clock? Where did you put the, where is the observer? Where is the clock? Depending on which position you put the clock. In other words, this clock, if you can you see that depend on x? Can you see? So the dependence of x is quite different. For example, if I draw the diagram here, so this is dependent of 2. If I just so this one, so this is just like linear function. Can you see? This is just like a gamma t, right? Multiply v gamma multiply c squared x, right? So the 2 clock is scaled by the gamma factor, okay? And so this time, this is the extreme case. That is when x equal to 0, okay? So this is a relation between t prime and t, okay? So if gamma is larger than 1, so the gamma is larger than 1, so t is, so that will be dependence. It's like this, can you see? So in other words, in this case, and t prime is always larger than t. You agree?
Yeah.
So this graph is special. In this case, x is equal to 0, right? However, if x is not 0, if x is not to 0, what would happen? So they have to edit something here, right? If x is larger than 1, you have to do the vertical shift. So although because this number is very small, because this velocity is very small, and you wouldn't be able to see this result. But there certainly they have some vertical displacement. Can you see?
Yeah.
So that is how to appreciate that. So that is x is larger than 0. Okay. And this displacement can be written as v gamma c squared multiply x. Okay. Of course, this difference is very small, isn't it? That is very close to 0. If v is smaller than c, can you see? Because this is a c square, can you see? This is c square. So therefore, normally you wouldn't. That is why you still can use the time dimension formula as we saw here. Can you see? However, basically, what I'm trying to show is that in order to discuss this twin paradox, and we have to rely on this Lorentz transformation rather than a time dimension formula. However, in high school, because they are not prepared to teach students a Lorentz transformation, therefore we can only discuss this issue by using the time dimension formula. So that is why you will see many cartoons, and when the twin return to the Earth, and one of train is getting older. That is because they just merely based on this cartoon, not experimental evidence. They just illustration of the outcome. If you only use the time dilation formula. Otherwise, as I show you, if you use the Lorentz transformation property, and you can show that there's no paradox. They age at the same time. It's very old issue. This discussion has been over a century now, and the reason is that you see everything seems strange from the special relativity. Do you know why? Because they have changed the old assumption, the common sense assumption that you see, if you travel, you wouldn't expect your clock change when you travel with airplane, right? But according to special relativity, it does. Only that change is very small. If the speed of airplane is not fast as the speed of light.
Oh.
Does that make sense to you now?
Yeah, it's just a weird topic.
Yeah, well, I think I don't know how did you introduce. I think many textbooks introduce this time dilation formula by using this diagram. Have you seen this diagram? They just do the use a triangle. They argue that, for example, if this is a train station, right? And if the train is passed by at high speed, so the train is moving at velocity v, right?
Yeah.
So if the clock is if this is so these observers have two observers, right? One observer A, another is observer B. So observer B is doing experiment. So what it did is that they got the flash lamp, the night, the turn on the night. Can you see? The turn on the night at t equal to 0. Okay, at this time, both they had their clock at the same time. See, so when can you imagine that at t equal to 0, this train is just passing this station. So because the night will travel vertically or upward. So this is the night will travel in that direction. You see. So the distance the travel will depend on the c multiply his time. Can you see? Yeah. So he got a clock here. This clock tell his time. And also he got a clock here. And the clock is indicated by t. All right. For the observer B, they see this flashlight just travel from bottom to from top, right? And that is how you can imagine the night travel very slow. Can you see? At constant speed, the night can travel from bottom to the top. However, for the observer A, the trajectory of the night will be different. Can you see? The night would travel in that direction. Can you see? Because the train is moving. Do you agree?
Yeah.
So when this B switch on the night at time 0, and the A saw the night beam arrive here, right? By the time the night arrived here, and then according to him, and that is how the night travel at the speed of light c, but use his own clock. You see. In the meantime, because this train is travel at this velocity, so therefore, can you work out this displacement? What is the distance between this horizontal displacement? Constant velocity.
ct squared minus not ct squared equals that.
No, simple, no, not square. It's just, you know the relation. I'm talking about this side. Yes, you're right. You're right. Yeah, I'm talking about this. This is just VT. Do you agree?
Yeah.
And this displacement is observed by A. And this night to travel along this hypotenuse, right?
Mm-hmm.
Yes, you are right. Can you write the equation over here about this event, about this experiment?
Yeah.
So that is how, that I think many textbooks, you introduce time dilation formula in this way without using Lorentz transformation. Yeah, okay, can you simplify to find the relation between the two T? Be careful, these two T are different, be careful. CT are not the same. Here, CT prime square are good, okay. Okay, can you simplify this equation to in order to find the relation between T and T prime? C square. Yeah, you can divide it by C square, good. Aha. We're looking for the equation of the T, and so we are looking for the relation between T.
Oh, mm-hmm.
Yeah. So you got a 2T here, right?
Mm-hmm.
You got T, you got a T. Can we put this T together? That's right. Okay. Are you sure? Where's the T? Ah, this is T square. Can I put the T square outside?
Mm-hmm.
If you square them on both sides,
Is that?
not quite, not quite. These two T are the same. Do you agree?
Mm-hmm.
Can we put the two T together? Ah, yes. I'm afraid this is not right. You see, how can you from here to here you factorize T?
Mm-hmm.
No, you can't.
Oh.
T and T prime are different. They are not equal.
Oh, I took the C out.
You took C out. Yeah, you can take it out.
And then I did T minus T squared because.
Oh, hang on. Can we just try it again? Can we just use V square, T square? Can we square first? We got a C square, T square, take C square, and the T prime square. Can we start from here? Can we just square up on both sides? So this is wrong. Can you see from here is also the wrong? How can you? You see, if you put a C square outside, you got a T square, take a T prime square. Do you agree?
Yeah.
If you square root, then that becomes C square root T square take T prime square. Can you see? So it's different. So this is different from yours. Can we just use this Pythagoras? This is correct. Although this is correct. Can we use this correct form? Can we square on both sides to get rid of the square root first? Okay. Now, can you simplify this relation equation? No, you're still trying to solve them, no? You see, can you see these? Can we put these two factors together? No? How did you get that? Interesting.
Oh, because this.
No. All of them is not right. This is wrong. Can you see? You have to. Can we use this right angle triangle? According to Pythagoras theorem, c squared t squared is equal to v squared t squared plus, right? C squared t prime squared. Can you either from this equation or from this equation? So this is question 1, this is question 2. To simplify this equation. Can you follow me? This is Pythagoras theory, isn't it? It's just a right angle triangle. Yeah, it's better. You separate, you put the same term together. So how do we simplify now? Yes, that's right. Yes. That's better. Let's have a look. T squared.
Oh, give me a sec, I forgot.
This is correct. You cancel the t. Where does the t go? Where is the c? Where is the c?
I cancel the c out because it's divisible.
No, I don't think so. How can you do that? You can divide by c squared. Can you write down here? Can you write down from over here? You got t squared equal to c squared, right? And c squared take the v squared and multiply t prime squared, right?
Yeah.
What you can do, you can divide the c squared. Can we divide c squared? C squared take v. That is the only thing you can do. You can divide the c squared. Okay. Make one. Okay. No. No. Can you see? Can you consider this is a? That is how to simplify the fraction. So these are two. There are one denominator. There's another denominator. How can I simplify these two terms? C squared. Yeah, that's one. The denominator became 1
minus v squared over.
That's correct. This time is correct. Yeah. So therefore, so what is, can we simplify this? Okay. Yeah, you get it. Yeah, you can see. You almost can see the factor now. Can we simplify? Yes, that's right. Do you remember that relation we obtained? T equal to t, the gamma t prime?
Yeah.
Yeah, that's right. You got the gamma here. Can you see? So this is a simplest, this is a simple way to derive the time dilation formula. Can you see? In other words, the time used by observer A is different. It's longer than the time t prime. You agree?
Yeah.
Because we know that gamma is always larger than 0. So when we see this formula, so t equal to gamma T prime. So since gamma is larger than 1, right? Or equal to, so therefore, which time is longer? T is longer than that, right? Can you see?
Yeah.
So how to interpret this formula?
Is gamma larger than 1?
Yeah,
Then
do you think
isn't
so?
T here it says like
Oh,
here?
it's the other way around. Yeah, other way, yeah. Yeah, so sorry, other way. So which is longer? Which time is longer? Does this side? No, I'm right. Is that right? Because you multiply if you multiply a number than that one, so the T is longer than T prime. Do you agree?
Yeah, but wouldn't this be the other way then?
You mean gamma is less than 1?
Yeah, because if gamma is bigger than 1, wouldn't not T be bigger than T?
Can we just take example, right?
Oh,
If T prime equal to 2, right? Gamma equal to 1.5. So what is the T? What is the T? Sorry. What would be the T?
oh yeah, I see.
That makes sense? That is another way to understand Einstein's simple outcome. Not a simple, but abstract outcome. Do you agree? So this is, if you use this formula, that T will be equal to 3, can you see? So therefore, T is larger than T prime. So what does that mean? So in this experiment, we know that the longer time equivalent to the time getting faster, right? The time is getting faster in this frame. Do you agree?
Yeah.
According to A. But on the other hand, if you just ask B, what would happen? If you ask the same question for the B, what would he say? He can use the same idea, right? He can use the same equation. So that is something interesting now. So you can see that this argument can be very confusing, right? So what I'm talking about, the result, the argument is dependent on which observer you use, right? So if that is the case, for example, this is observer A, right? He got a clock, which is called a T, and observer B, he got a clock, which is called a T prime, right? According to the time dilation formula, he's moving, so this velocity is moving. So in this case, the train is moving according to A, isn't it? So the observer, can we just write the whole story here? Okay. So according to observer A, right? And number 1, B is moving. Do you agree?
Yeah.
B is moving. And number 2, what is the time? And his time is shorter, right? So T prime is shorter than his time. Do you agree? Toward the right, okay? Toward right-hand side, okay? Right-hand side.
Yeah.
How about observer B would talk about this issue? That is the relativity all about. You have chosen different frames. So this is a frame B, right? So this is a frame A. Now, this time, if you ask observer A, what would you say? First of all, who is moving?
Observer A.
A is moving, right? To the left-hand side, see?
Yeah.
Okay, how about their time?
The T naught would be bigger than T.
Same result, right? Because we only have one formula, right?
Yeah.
So the result is the same. Do you agree? Is that strange?
Yeah.
So which clock is slower? Can you answer the question?
They're both right, aren't they?
The moving clock is slower.
Oh yeah. Yes. No, the single clock is slower.
So there's something absolute. Do you have? Can you see? That is how we use Einstein. If you use the time dilation formula, this relation is absolute, right?
Mm-hmm.
T is equal to T prime divided by this factor. But which clock is slower? Obviously, the clock is not moving.
Mm-hmm.
Or so what conclusion can you make from here? So which clock is the moving clock is slower or
The moving clock is faster. Oh,
yeah.
both clocks are moving in different frames.
You see, you have this we are confined to the result we just obtained here. Can you see?
Mm-hmm.
So this is the result that we got T prime. T prime is the clock, B's clock, right?
Yeah.
And from this result, because gamma is larger than 1, so therefore, and the T is longer than T prime, right?
Mm-hmm.
So in other words, his clock is always slower, you see?
Mm-hmm.
Even according to the B, do you agree?
Yeah.
Does that make sense or not?
Um.
Because according to the B,
Oh.
this clock is moving, you see?
Mm-hmm.
So they return to the twin brother. So which clock actually slower from your impression?
B, yeah, the moving clock.
Is slower, right?
Mm-hmm.
So does that make sense now? Or
Yeah.
confusing?
It's confusing, but I think I sort of understand it.
You sort of under this paradox now. That is yeah. Sometimes when you solve this, when you consider this relativity issue, you have to accept the formula first, right?
Mm-hmm.
You have accept one clock is slower than others. And do you think you can use this time dilation formula alone to discuss the paradox exists?
No.
Why not? Because it's
Well,
yeah.
Well,
It's other way around, isn't it?
mm-hmm.
So when they meet, when they finish the journey, which brother is older than others?
A.
A is older, right?
Mm-hmm.
According to this formula, yes. Okay.
Mm-hmm.
So you can see that depending on how you use the which formula do you use to discuss that. We know that this discussing the method that we show you, this is Pythagoras in the Pythagoras theorem method, can explain somehow to some degree, but compare they are not as reliable or accurate as a Lorentz transformation.
Yeah.
So, well, keep using this formula then. At least you can tell people something which is unusual and strange, right?
Yeah.
But don't worry, because this is just very strange due to the assumption that light travel at a constant velocity, right?
Mm-hmm.
If you accept that assumption, and you are obliged to change all these conventional experience.
Mm-hmm.
That is why.
Yeah.
Well, I think that is up to you, right? You can
Mm-hmm.
reject or accept, doesn't matter, depending on how to approach this issue. Okay.
Yeah, and like in real life, it's not really important because
It's not important. It's not
yeah,
important.
because we're so much under the speed of light that it'll.
And also in the real, if you want to do a real experiment, you have to consider when you speed up the train, and then it's no longer the frame of inertial frames. And some people have go so far to consider when they go to the other side of journey, they have you slow down, turn the direction, and speed up, right? In this all process, you cannot use Einstein's special relativity because you are dealing with non-inertial frames.
Yeah.
You agree? So it's endless. The discussing is just endless, depending on how to figure out figure out the conclusion.
Yeah.
But just be prepared. Always something very strange. If you accept his assumption. That is why few people understand relativity. Not surprised. Okay. So I save this and okay. Okay, see you next time.
I'll see you next week.
Okay, goodbye.
Bye.
Goodbye.